Today we study alternating current. First, let us consider the energy flow in harmonic oscillator. Harmonic oscillator consists of a spring with spring constant K and mass M, and there is an equilibrium position that is selected to be origin, and displacement from the equilibrium position, we denote the displacement to be x. Then the F equals ma, mass times acceleration is the force, and this force is opposite to the displacement, which is kx. We move minus kx to the left side, and divide both sides by the mass. Then we have this expression. This differential equation has the solution e to the I omega 0 t and e to the minus I omega 0 t, or cosine omega 0 t and sine omega 0 t. These two and these two are linearly independent. Sure, the omega 0 is the characteristic angular frequency, that is square root k over m. The solution of this differential equation is linear combination is these two, or linear combination of these two contributions. Before we go ahead, we first consider the chain rule. A to the n time derivative is expressed like that. Therefore, a squared time derivative to a dot. In a similar manner, this time derivative is 2a dot times a double dot. We have x double dot plus omega 0 squared x equals 0. We multiply x dot. Then XX dot is this. X dot, X double dot is this. Therefore, if we substitute these into this equation, then we find this 0. Because omega 0 squared equals k over m, we can rewrite this This is kinetic energy, and this is the potential energy. And sum of this is total mechanical energy. So total mechanical energy is conserved. So we consider a simple case. Initial condition at t equals 0, the position is x0 and velocity is 0. Then the solution is C1 cosine omega 0 t x of t, C2 plus sine omega 0 t. X of 0 equals C1 x dot of t equals minus C1 omega sine omega 0 t and C2 omega 0 cosine omega 0 t. We substitute 0 this is 0, this is x 0. Therefore, the solution is completely determined as x0 cosine omega 0 t. Then we can compute the velocity we can compute the kinetic energy and potential energy. Sum of these is, because cosine squared, sine squared, they are in phase, they have same argument, omega 0 t, so the sum is 1. So for given conditions, we have the sum of the kinetic energy and potential energy, that is total mechanical energy, is conserved. If we draw a plot, we have this kind of form. Next, we consider the energy flow in Rlc oscillator. Rlc oscillator has the equation if we follow the current, the potential difference for the inductor, potential difference for the capacitor, this one should be 0 because there is no battery. Multiplying minus 1, we have equation of motion. Divide both sides with L inductance. Because I is derivative of charge, is double time derivative. Equation is equivalent to the simple harmonic oscillator. Simple harmonic oscillator, omega 0 was K over M square root, and the LC oscillator, LC. We use the same method to find out this amount is conserved. We have 1/2 Q dot square plus 1/2 LC Q square time derivative equals 0. Multiply L. Q dot is I, current. This is the magnetic field energy. This is electrostatic field energy. The sum of the magnetic field energy and electrostatic field energy, magnetic field, this contains electric field. Sum of them should be constant, just like the total mechanical energy conservation in a simple harmonic oscillator. LC oscillator is mathematically equivalent to the simple harmonic oscillator. Let us continue to look at the electromagnetic oscillation. Electrostatic field energy, 1/2 Q square over C, or Q equals to CV. Magnetic field energy is 1/2 Li squared. The sum is the energy, sum of the electric field energy and magnetic field energy, that is constant of motion. Equation of motion for the LC circuit is equivalent to the simple harmonic oscillator. The only difference is the explicit value for the characteristic angular frequency. This is the solution. For example, if we substitute x0, t equals 0, this one is x0, and sine 0 is 0. And if I take the time derivative, x dot of t equals minus x0 omega 0 sine omega 0 t plus v0 cosine omega 0 t. If we substitute t equals 0, x dot 0 is v0. That's correct. So this is the general solution satisfying the initial condition. In a similar manner, charge Q saved in charge Q is defined for the charge saved inside the parallel plate capacitor of an LC circuit that can also be expressed in a similar form. We need to put omega 0 here. In summary, simple harmonic oscillator and LC oscillator, the displacement, charge, mass, inductance, spring constant, 1 over C, they are analogous to each other. Characteristic frequency is square root to K over M, square root 1 over square root LC. Kinetic energy and potential energy. They are equivalent to magnetic field energy and electrostatic field energy. This is related to the solution. In case we have charge Q is of the form, for example, we have cosine omega t, A cosine omega t plus B sine omega 0 t. Then it can be expressed as and we can say this is this one and this one squared. These are can be expressed as a cosine delta and sine delta because square of the two numbers equals 1. Then this one can be parameterized by cosine omega 0 t minus delta. So the solution for Q can be expressed as a single sinusoidal function including phase. This one was minus the delta, just what we have found. So using this, current can be computed. These numbers are all omega 0. Next, we consider damped oscillation in an RLC circuit. In an RLC circuit, according to loop rule, because there is no EMF, the potential shift due to the EMF is vanishing, and then following the current, potential shift in this inductor is minus L di over dt, and potential shift when we pass through the resistor is minus IR, and then potential shift when we pass along the current is Q over C for the capacitor. We multiply minus I to find the equation of motion. Because I is a time derivative of charge, where charge is the charge Q saved. This is Q and this is minus Q. Saved inside the parallel plate capacitor. We multiply 1 over L to find this equation and use this relation. We have this equation. This is equivalent to the damped harmony oscillator. Damped harmony oscillator has the equation F equals minus Kx minus Bx dot. Here B is the damping coefficient. F equals ma. This equation becomes divide both sides by m. And we define gamma to be B over M, omega 0 to be square root K over M. Then we have equation x double dot plus gamma x dot plus omega 0 squared x equals 0. So in a similar manner, we define gamma to be R over L, omega 0 equals 1 over square root Lc, then Q double dot plus gamma Q dot plus omega 0 squared Q equals 0. So the Rlc circuit is simplified into x double dot plus Q double dot plus gamma Q dot plus omega 0 squared Q equals 0. That is consistent with the damped harmony oscillator. In a similar manner as we have done with the simple harmony oscillator, we multiply Q dot on both sides. Then equation becomes like that. And we remember Q dot Q double dot equals time derivative of 1/2 Q dot square, and Q dot is the time derivative of 1/2 Q squared. So we use this relation. The sum of the first two terms No. Sum of the first and third term is this, and use these two identities. We have 1/2 Li squared and 1/2C Q squared. This is the magnetic field energy, and this is the electrostatic field energy. Therefore, this equation is simplified as, of course, minus R Q dot square I squared. This is minus Ri times I. This is a potential loss due to the current passing through the resistor and the charge supplied to the resistor per unit time. So this is a power loss. The electrostatic field energy is lost with the rate, the time rate. Therefore, power of a resistor is IR squared, I squared R, and I squared R is the amount of energy consumed by a resistor per unit time. This we have already discussed the equivalence of the Rlc circuit and damped harmony oscillator. Let us investigate the solution for the damped harmony oscillator. We have the second order linear differential equation where the factor gamma is the resistance divided by the inductance, and characteristic frequency of the simple harmony oscillator is 1 over square root LC. The solution of this linear differential equation can be found by substituting Q with the exponential function. If I substitute this exponential trial function, becomes lambda squared gamma lambda plus omega 0 squared e to the lambda t equals 0. Exponential function never becomes 0. So we can divide both sides with this to find out the quadratic equation for the lambda. We say the lambda to be the eigenvalue. The solution for this quadratic equation is this. Here, if gamma squared minus 2 omega 0 squared, so it is inside the square root we say this discriminant. If the discriminant is positive, then lambda are both real. Two real solutions. For lambda. So D is a positive. In case D is a negative, if D is negative, then we have lambda equals minus gamma plus minus I square root 2 omega 0 square minus gamma square. So, two complex solutions. If the discriminant D equals 0, lambda minus 1/2 gamma is a double root. We say this is this exponential real and imaginary part, this is oscillating. So we say this underdamped case. There is no oscillation, two real solution. So the damping is very strong. Damping factor is large. So overdamped. In between, at the border, on the border, it is critically damped. So we consider underdamped, overdamped, and critically damped. And the most important case we are interested in this underdamped case. Let us consider the underdamped case. Underdamped case, that is characteristic frequency omega 0 for the simple harmonic oscillator. This one is greater than 1/2 gamma. And because we are interested in the Rlc circuit, this omega 0 equals 1 over square root Lc. And gamma equals R over L. There are two complex eigenvalues for lambda. Let's see. If 2 omega 0 is greater than half of gamma, we can flip the order. 1/2 minus gamma plus minus I square root 2 omega 0 square minus gamma square. This one is minus 1/2 gamma plus minus I omega 0 and square root 1 minus 2 omega 0 gamma square. We say this one to be omega prime. So solution is a minus 1/2 gamma plus minus I omega prime, and omega prime is omega 0 square root 1 minus gamma over 2 omega 0 square. We substitute these numbers, gamma over 2 omega 0, gamma 2 omega 0. Therefore, gamma over 2 omega 0 squared is R squared C 4L. And omega 0 is 1 over LC. The solution, general solution for this homogeneous second-order linear differential equation is a linear combination of the two exponentials, e to the lambda plus t, e to the minus lambda plus lambda minus t with arbitrary constants, and lambda plus and minus are given in here. So we can express in either in exponential form or cosine plus sine. The overall factor, overall exponential factor, exponential minus 1/2 gamma t is factored out, and inside the linear combination and cosine and sines with the arguments of omega prime t and omega prime is given in here. We notice that gamma over 2 omega 0 square, this is less than 1. Therefore, square root 1 minus gamma over 2 omega 0 square, this is less than 1, between 0 and 1. Therefore, omega prime is less than omega 0. Period t for the simple harmonic oscillator is like that. This underdamped motion is not a periodic motion, but if we consider the oscillating factor that are factorized, this factor is a periodic with a period t prime, omega prime over 2 pi. Because of this, the period of this oscillating factor in the underdamped motion is longer than the original period for the simple harmonic oscillator. For example, we consider a simple case. The object, the mass, is at the origin at t equals 0. Then we have this kind of expression. At t equals 0, it is either sine or cosine, but for a simple case, at t equals 0, exponential is 1, d1 cosine omega t. d2 sine omega t. So this one vanishes. If it is 0, then d1 equals 0. If d1 is 0, then we have only d2. We have substituted d2 to be xm. So this is a special solution for an underdamped case. We can take the derivative of this to find the velocity. Then we can take the derivative of this exponential function or this sine function. Sine function gives a cosine with additional factor omega prime. If we take the derivative for the exponential function, we have minus gamma over 2 and sine is invariant. Therefore, if we substitute t equals 0 in this expression, then velocity at t equals 0 is xm times omega prime. This solution corresponds to, let's consider another case. If x0 is given like that and velocity at t equals 0 is given as v0, then you can find the solution is simplified as this. You can make use of this to find out x0 equals x0 and take the derivative and substitute t equals 0 to fix this. Then you have two conditions. You have two linear equations for d1 and d2, and d1 and d2 are completely determined as this. Using this, a little bit complicated, but we can in principle find out the velocity. We return to a simple special case. And a spatial value. For example, omega 0 is 2 pi hertz and gamma equals 1 hertz. And gamma over 2 omega 0 equals 1 over 4 pi. That is much less than 1 and greater than 0. Therefore, this is an underdamped case. We draw the plot for x of t. In units of xm. We find that exponential function is here. That exponential function is exponential minus 1/2 gamma t. Our solution, this solution is given here. The local maximum does not exceed the exponential function. So it's oscillating, but the range of oscillation is decreasing. It is decreasing as t goes to infinity. And it saturates to 0 as t goes to infinity because of this damping factor. And this brown curve represents this corresponding simple harmonic oscillator, whose range of oscillation does not decrease because the energy is conserved. Let us continue to consider the same problem. The spatial solution for underdamped motion with the same parameters. We use the solution, this solution, and it's a time derivative to find out the kinetic energy. Kinetic energy 1/2 mx dot square, and the potential energy. The sum of these two is the total mechanical energy, K plus U. Here, the blue color is the kinetic energy of the particle. As you already have seen, Xm is like that. So velocity is maximum at the starting point, and t equals 0. Potential energy is U equals 0 because x0 equals 0, and kinetic energy is a maximum at t equals 0. The kinetic energy decreases to stop. This is the turning point. Increase, decrease, increase, decrease, oscillates. The potential energy is 0 at t equals 0 and increases. The maximum turning point and return oscillates. And sum of these kinetic energy and potential energy is the total mechanical energy. The green curve is the total mechanical energy that decreases monotonically as time goes on. Because this is the initial total mechanical energy. Initial total mechanical energy. So total mechanical energy decreases. Therefore, the loss of energy increases as time goes on. And the lost energy, when t goes to infinity, lost energy becomes the total initial value of the total mechanical energy. So as t goes to 0, x dot equals 0, and it reaches the point, x goes to 0. As t goes to 0, x and x dot, both of them, approach 0. Next, we consider the same problem, but we are interested in the period of oscillating vector. This curve represents the oscillation of x of t, x0 of t, that corresponds to sine omega 0 t. Because the sine omega 0 t has a period and omega 0 equals 2 pi hertz. It is 1 second. So when the oscillation returns to the original phase, it takes, this is a unit of second, 1 second for the corresponding simple harmonic oscillator with the characteristic frequency 2 pi hertz. But as we can see in this figure, this damped motion has this amplitude is a product of 1/2 gamma t multiplied by sine omega prime t. It is not a periodic motion. So it has a damping factor and oscillating factor. The period of this oscillating factor, T prime, is 2 pi over omega prime. And omega prime, if we substitute these values, this is 1 minus 1/2 squared, so square root 3/4, this is square root 3 over 2. Therefore, omega prime over omega 0 is 1.7 something divided by 2. Omega 0 this is second. That means when it returns to the origin, here is somewhere around here. T prime. T prime is greater than 1 second. This is T. T equals 1 second. When it returns to the origin without a phase state, this is pi, so this is delta t is delta t. Delta t prime equals 1/2 of period of that oscillating factor. That is half of this second. That is approximately 0.577. The point is here. As we can see, in comparison with the T and T prime, the period of oscillating factor is bigger than the corresponding value for the simple harmonic oscillator. The remaining two cases are over-damped motion, with both characteristic values. The eigenvalues are real, and two real values, but they are identical to each other. A double root. In both cases, no oscillation. No oscillation. This is called the over-damped case, and the double root, we have critical damped case. The solution for the over-damped case, because we have overall factor, this damping factor, original damping factor is the same, but there's an additional exponential. It can be either exponential gamma prime 1/2 gamma prime t, or minus exponential gamma prime t, or cosine hyperbolic and sine hyperbolic. In case of critically damped motion, it has additional factor. This one and t. There are two linearly independent solutions for the double root case. Let's consider forced oscillations of three simple circuits. Three simple circuit is RC, RL, and simple harmony oscillator, LC, and combining everything all together, RLC. What happens if we apply EMF of alternating current? Alternating current is AC. In case we apply a battery, this EMF is DC, direct current. So DC and AC. In Korea, frequency is 60 Hertz. So omega equals 2 pi f. So 2 pi times 60 Hertz. The reason for using the alternating current is actually the electricity is generated based on Faraday's law. Changing magnetic flux give rise to the EMF, and changing magnetic field is easily made by applying both poles of fixed magnet. Between fixed magnet, the axis is rotating using turbine, and the axis that is connected to a wire that passes to which the magnetic field can pass, and this rotor rotates, then the flux phi b passing through this circuit changes depending on time because the axis rotates. And if it is rotating with the uniform circular motion, a fixed angular frequency, then the generated electricity has the time dependence of sine, either sine or cosine omega t. We say this driving force oscillates with angular frequency omega d. So we put the d on omega for the driving angular frequency. The natural frequency of a circuit that contains the inductance and capacitance has the natural frequency, natural angular frequency omega 0, and when the driving force is applied with an AC current, the driving frequency does not have to be the same as omega 0. We shall find that there is a resonance. That means the driving frequency dependence appears in the amplitude for the current I passing the resistor, and the maximum value is achieved when the driving frequency is the same as the characteristic frequency of the circuit. That is called resonance. When the driving force is applied, without driving force, damped harmonic oscillator is a kind of linear differential equation where L is the second order linear differential operator. We have non-vanishing value on the right side that depends on the driving force. Or driving EMF in the circuit. That gives rise to additional potential, external potential. The solution to this equation is general solution to this equation is the sum of the particular solution that gives correct value for the right hand side, added by a linear combination of two linearly independent solutions, x1 and x2, that are the solutions for the corresponding homogeneous equation. So xh is the solution of this, and x of t is the sum of particular solution plus general solution for the homogeneous equation, and general solution for the homogeneous equation is the linear combination of the two linearly independent solutions for the homogeneous equation. And this is non-homogeneous. If the operator is nth order linear differential operator, the still particular solution is obtained in a similar manner, and the homogeneous equation solution is a linear combination of n linearly independent solutions. Let us consider the driven Rlc circuit. This is E. Direct current we use is E only, but in alternating current, for example, cosine omega t here, to distinguish this frequency from the characteristic frequency omega 0, we use the D. That stands for the driving force, driving frequency, driving angular frequency. We divide both sides by L and replace this 1 over LC with omega 0 squared, and replace R over L with the coefficient gamma that involves the damping, and simplify this epsilon 0 E0 over inductance with A0. We have this non-homogeneous equation. We notice that gamma, omega 0, both of them are real. Suppose that we have an equation that has x that is a real, and another equation with the sine omega t instead of cosine. Again, y is real. We multiply I to the second equation and add them up. Then, because this gamma and omega 0, they are real, A0 is also real, we can combine these two as z equals x plus iy. This equation, sum of this equation becomes this. And actually, A0 does not have to be real. Anyway, e to the I theta equals cosine theta plus I sine theta. Hence, it is possible to solve this problem in a complex space. The good point of this method does not care whether it is cosine or sine. If I want to find out the cosine case for driving force is related to the cosine, then we end up with taking the real part of EI dt. If I want to solve the problem for sine, we take the imaginary part of this. Because gamma and omega 0 are all real part of this is x double dot plus gamma x dot plus omega 0 squared x. Imaginary part of left hand side is y double dot plus gamma x y dot plus omega 0 squared y. Anyway, we first solve this problem first, and then depending on the situation, whether the right side is cosine or sine, we just take the real or imaginary part. So let us solve this problem. Again, it must be a linear combination of particular solution and the linear combination of two linearly independent solutions for the homogeneous equation. The lambda 1 and lambda 2 are solutions for this eigenvalue equation. We already know that there are three cases: underdamped, overdamped, and critically damped. Underdamped, overdamped, and critically damped case. The only thing we need to consider additionally is the particular solution. In any case, as t goes to infinity, all three solutions for this homogeneous Z homogeneous goes to 0 because of the exponential decay factor. Here too, but exponential factor. Here, gamma prime is always gamma, less than gamma. Therefore, this additional factor does not change the trend as t goes to infinity. Therefore, as t goes to infinity, we are end up with a solution, particular solution only, and the homogeneous equation solution disappears. Substituting the result, trial solution, e to the I omega dt, z particular, equals some amplitude A, so amplitude A, and this. And we have this vector, and what is this? Time derivative, z double prime I omega d, z double prime p minus omega d squared a exponential I omega dt, exponential I omega dt. So if we substitute all these results, we can find this relation. Now this factor, common factor, can be divided, and the amplitude can be found by solving this linear equation. This vector can be divided in here, and this complex number, simplified complex number, we multiply its complex conjugate up and down. This is just 1, and it becomes absolute value squared. So A plus IB, A minus IB equals A squared plus B squared, something like that. So square, square. And this one appears in the numerator, and A0 over a vector is placed here. Finally, we can determine this numerator contains the phase vector, phase I, and we have minus I, so we have exponential I5, and absolute value appears in here. Therefore, particular solution is completely determined as this. And if you are interested in the real part, it gives a cosine. Imaginary part, it gives a sine. And this is for E equals A0 cosine omega dt, and equation corresponds to A0 sine omega 0 t. We find that there is a phase shift by minus phi that is determined by this relation. Okay, you can apply this to find out the condition for maximizing the amplitude, and special case for the maximizing the amplitude is this relation, and maximizing the amplitude for the current, in that case omega d is multiplied due to the fact that current is the time derivative of charge. That result gives driving frequency becomes the characteristic frequency. As you can see, when you reach omega d goes to omega 0, there is a peak, and the peak is magnified when gamma small. So when gamma is omega 0, it is very small. So here, this one, gamma over omega 0 is 1/20th. This one is 1/10. This is 1/5. This one is 1/2. And gamma equals omega 0. As you can see, when gamma is small and driving frequency reaches omega 0, the output voltage across R, because current I passes the resistor, and resistor has the voltage proportional to the current, and that output voltage across the resistor is magnified when you reach the resonance frequency omega d goes to omega r, that is omega 0. Okay, that is a resonance. Okay, that's it for today.